All right, hello everyone. My name is Mark Roth, and since I work for a high-tech investment manager, I'm obligated to tell you not to listen to me about anything that's financially related advice, so don't take anything I'm about to say as solicitation or anything to go invest. All right, so J.R.R. Tolkien wrote The Lord of the Rings, and in that novel, he created a creature called an Ent. He's actually a linguist, and he loves creating languages. If you look at his works, he's created, I think, 2 different languages for elves. He's created languages for dwarves, and the Ents actually had their own language called Old Entish. And this language was very peculiar in that the names of things in that language refer to their full story of how they came to be. And because of the deep lineage of these creatures, saying the name of one of these creatures could take you several minutes. And when you hear that name, though, you know exactly who it is you're talking about. There's no ambiguity. And so the Ents would say, don't be hasty. It led me to wonder, what if we actually used Old Entish names to talk about our data sets? Would that kind of built-in provenance about the name of the data set make it so that it would be more likely we could reproduce research? Let's find out. So Memento was created by 2 Sigma as a way for remote researchers who were helping us to submit their data pipelines. And Memento is not so much an implementation as it is an idea. It's a set of ideas about how to organize your research. And when you use Memento, you get a few things out of it. First of all, you get the ability to more accurately maintain and communicate provenance about your data. You get better reproducibility for your data sets, so it makes it easier for someone else to continue your research from where you left off. And you get better ergonomics. So it's possible to make more efficient use of your time, and also to reduce the amount of cost that you have in paying for your research, because you never have to compute the same data twice. Now, I'll make a claim that on some level, these 3 things, provenance, reproducibility, and caching, actually all have to do with naming. And I'll explain why in the following slides. But first, it takes me to my first point, which is that naming is hard. It's a hard problem. In fact, most of us know that there are only 2 hard things in computer science: cache invalidation and naming things, and off by 1 errors. And Memento helps with 2 out of the 3. So to describe Memento, it helps to look at it in the context of a realistic research problem. In 2013, New York City created or launched its bike sharing program called City Bike, which is now the nation's largest bike sharing program and an essential part of New York City's transportation infrastructure at this point. Those who are Bostonites will point out that, yeah, but we had it first with blue bikes coming out in 2011, which is not the nation's largest, but still a very important part of Boston's transportation infrastructure. But you may ask yourself the question, are these bike sharing programs equitable? And to answer that question, you might, if you want to do it scientifically, you might start with a hypothesis, which might be zip codes in New York City with higher median income show higher city bike usage. And you could then prove or disprove this hypothesis by starting with the data and then forming a data pipeline and doing your research. So let's take a look at what a data pipeline might look like for this hypothetical research scenario and see how Memento would apply to it. But first, let's start at the end of the data set. Imagine that you have a paper talking about or discussing this hypothesis, and it's accompanied by a data set. And you take a look at the data set, and it's a data set called 2020.csv. The name of that data set isn't very helpful by itself. Now, you might open it up and look at the column names, and if you're lucky, maybe it's in Dataverse or something, and you can get some additional information about provenance and things like that. But if you're tasked to continue this research, to sort of pick up where it left off, you're going to need more than that metadata, and you're going to have a bunch of questions. First of all, you might ask, what are the original data sources? What methodology was used to process this? Where are the intermediate artifacts, not just the final one, but all the ones that led up to it? Can I reproduce this data? And how am I going to generate data for 2021? So let's take a look at the pipeline step by step. And I'm going to ask some naming questions along the way. First, we start with the raw data. So if you're looking at city bike data, it exists in an Amazon S3 bucket called trip data. Now, first of all, I think this is a little bit presumptuous of city bike to grab the name trip data, as S3's namespace is global. So they're basically claiming the name, saying, we are the world's providers of trip data. But let's take a look to see if we can do a little better with the naming in our own pipeline. I'm going to do a quick audience poll here. I'm going to give you 3 names for ingesting the city bike data. So the first one might be more technology-centric, like ingest S3. You pass a URI and a path regex. Second one might be pipeline-specific. So we're going to say step 1, ingest data. And the third one might be more dataset-centric, ingest city bike. So how many of you here would choose A as your name? How about B? Okay, and how about C? Wow, a lot of C's. How about it depends? Yeah, of course, yeah. So it does kind of depend, right? And but I'm actually pleasantly surprised to see lots of people. I think this audience really understands the importance of naming. If we name it based on the data set, there's some advantages, but of course there are some trade-offs as well. I'm going to pick C as well. That's the one I decided to pick. We have to name the CSV files as well, which is a challenge in and of itself. Actually, the raw data set files as well, which is a challenge in and of itself. And now we're going to go to the next step where we're going to process the data and turn it into just raw structured columns. Not raw, but structured columns. They're taking the raw data, turning it to structured columns. So I'm not going to poll you this time, don't worry, but we have 3 other possible names here. And the point that I'm really making is that as you're building this pipeline, there's lots of things going through your head as a researcher, like what am I going to name this? How am I organizing my research? And one thing that we noticed when we were building Memento is that researchers who are better organized in how they name things in their notebooks and how they organize their research tend to produce results that we were much more easily able to reproduce in 2 Sigma. So in this case, I'm going to pick C again. And we've got a couple of CSV files here. And what I want you to notice is that in this particular workflow, I'm not saying that they're all like this, but as the pipeline progresses, the naming actually gets less and less informative. Even though we're making an intentional decision here to try to capture things, we're choosing C every time, the data sets are becoming less and less informative in their name. And this is especially so in the last step, where we're joining these 2 data sets together. And the only thing they really have in common is that they're both for 2020. So whoever wrote this pipeline wasn't even trying, and they just named the last stage 2020.csv. This is inspired by a real-world example, but it wasn't exactly the same. Okay, but let's take a look at the pipeline as a whole, and you can see that 2020.csv doesn't tell you nearly anything about the rich history of what went into this data set. And this is a very simple pipeline. Pipelines can get much, much more complex than this. Now, of course, once the pipeline is done, we're done, right? There's nothing to worry about. Well, we all know that's not true because the only constant is change. So what if IRS.gov, in this case, where we're getting our median incomes, they decide to issue a correction to the data? How do we know whether 2020.csv has incorporated that correction or not? What about if we fix the normalization logic at one of the stages? Or we have a new tolerance parameter. I mean, the name is in the CSV, but why not the tolerance parameter? What if I chose 3 different values of the tolerance parameter? Which one did I end up publishing with? What if there's a new file format upstream? Or what if one of the stages was run on an AMD machine instead of Intel, and that produced quantitative differences in our pipeline? All these kinds of questions are not captured at all by the name. So there's got to be a better way, and I think that our friends, the Ents, might be onto something here. So I've been at 2 Sigma a long time, and I've had a chance to see a lot of different clever research hacks, I'll call them. And one day I saw a request come in. I was managing a storage system. And they said, can we increase the length of the column names in the file? And I said, why? 256 characters should be enough for anyone. But then when I sat down with the researcher to see what they were doing, I was shocked. They had a column name that looked something like this. Imagine this was a column name and not a CSV name, but the same idea. But as I sat down with them, it started to make more and more sense, because what they had done is devised sort of an RPN-style naming scheme where every single stage of their pipeline was captured in the name of the data set. If you wanted to know whether this data set was used with a 0.7 tolerance join parameter, it's right there. There's no guessing. There's no ambiguity. So I would call this sort of the entish name for their data set, if you will. But I don't see many people doing this. Why? Well, it's not very practical, is it? It's like kind of difficult to write this way. But I'd say that this researcher, and ENTs in fact, would have saved themselves a lot of time if they knew about hashing. And so let's talk about Memento's approach. So Memento does this in a little different way, as you might guess. But what's interesting is that Memento doesn't have you deal with data sets at all. The philosophy of Memento is that the function is the data. In other words, the computation that you provided that you did on the data represents the data itself. This is a very functional approach. So if you want to know where is the data set with the 0.7 tolerance join parameter, just call the function again with 0.7 as the tolerance parameter. If it was ever computed before, you get the answer immediately. If it wasn't computed, it's going to go off and compute it with that tolerance parameter, and now it's available for anyone in the world, or in your team at least, to be able to see the results of that computation. Now, the name join city bike wealth is actually just a symbolic name. It's not a real name. The true entish name for this data set is its hash. But we all know that hashes are a one-way function. So if we use this hash as the name, how do you know what actually happened? Well, what we do is that every time you call one of these functions, you get a keepsake, or a memento, if you will, of what the value of what were all the criteria that went into that calculation at that time. So let's take a look at how the memento approach would work for this pipeline. We start by just basically nixing out all the data sets. We don't really need them anymore. In fact, they're kind of a liability. As soon as you serialize the data to disk in that way, they can get out of sync with your pipeline. So we take them out. And it already simplifies the pipeline quite a bit. Then we have durable storage to worry about. This is something I didn't really talk about before, but when we ingest the data, when we pull in data from S3, from wherever its raw source is, you don't know as a researcher whether that source is going to be there forever. You don't know the durability of that data. And so I would argue that as we publish research papers, it's important not just to include the names of the data sets, of the final, it's important not to just to include the last stage of the data set, but also any of the raw data sets you consumed as part of your research should be made available with your research paper, just in case those data sets disappear. So Memento does this for you. Whenever you ingest data, it gets copied to durable storage. The other thing that Memento does is it hashes all of the code in your pipeline. It assigns hashes to these things in such a way that whenever you change the function, you automatically get a new hash for that function, meaning if you change the source code for that function. It also changes the hash of anything downstream that consumes that data automatically, because this joining function will produce different results if one of its dependencies produce different results. Now, when you actually go to call the stack of functions, the other thing we hash is the runtime environments, just in case the architecture changed. So if you go to join this data in the end, if you want to call the join function in the end, what you end up with edges, which are actually the calls to these functions. And these edges are also given a hash. And it's these edges that are actually the true entish name of the data set, because it contains the bound parameters in them as well. And these are the things that the mementos are generated from. Let's take a look at what goes inside of a memento. So the Memento is effectively a document, and it contains metadata, including the time of invocation, the runtime, who ran it, the lineage. It also includes the inputs, so the version of the function, the parameter map, the dependency set, runtime environment, and the outputs. Not the output itself, but a hash, a link to the output. The output wouldn't fit in the little box. These mementos can actually be signed, giving them integrity, so that you know who performed the computation. And in fact, because it refers to all of the dependencies, you can construct a signature chain all the way back to the original raw data source. So now that we looked at this, let's take a quick look at what Memento can do for you. So as I mentioned, all these things are really about naming. So provenance, I would claim, is about naming. To understand provenance, we want to know what raw data was used, when was it ingested, which parties were involved in the ingestion, what was the methodology. And it turns out that all these things are actually accurately named by Memento. Mementos provide high fidelity end-to-end provenance by capturing all the information about what would make provenance different. And I'll point out here that Memento is not just an implementation. The idea translates beyond its current implementation. We can consider this as a standard. And I dream of a day where whenever you request a data set, you also want to know the memento that comes with the data set so that you understand where it came from. And in fact, because you can adopt this to multiple frameworks, this can really be done in a hybrid way, where you might have different stages of your pipeline using different technology stacks, but you can still have one chain all the way back to its raw data source. Reproducibility is also about naming. So to reproduce data, you need all these things to be accounted for. The only thing that Memento doesn't handle here is the use of non-deterministic libraries or hardware, but it does give you some tools to deal with that. So Memento accurately names all the things that are involved in reproducibility, and it records everything you need to know to reproduce research. And the results can be signed and validated by third parties. But what's interesting is that it doesn't stop there. There's more. It provides some ergonomic advantages and economic advantages as well. You can relax and make good use of your researcher time by just writing the functions, and Memento will take care of the serialization, the storage, the naming, the true naming of all this information, and keep your research organized. It also allows you to, whenever your kernel restarts, to continue your research from where you left off. You don't have to worry about which cells to re-execute and which files to sort of. I come from a family of teachers, so. Okay, so I guess nobody will forget this talk. Apologies. Yes, you'll all have a little memento keepsake of this talk in your eardrums. So thank you so much for bearing with the AV issues, and I've only got a few more slides, and then I'll take some questions. But as I was saying, so Memento gives us several ergonomic and economic advantages. So first of all, Memento helps you be more productive by keeping you organized. And you can just relax, sit back, and write some functions, and Memento will take care of serialization, it will take care of organizing your artifacts, and it will also ensure that when you restart your notebook kernel, it will automatically restart your research from where you left off. So you don't have to worry about which cells to execute, how to store your data in files and kind of read them. At least when I've done research, that's been always a point of like just organization overhead, right? So the interesting thing here is that Memento, in order to cache things, you need to invalidate your cache. And if you remember, caching is the other hard problem in computer science. And that's because of cache invalidation. You don't know when you need to invalidate your cache. But if you think about when you need to invalidate your cache, it's whenever the code changes, whenever the parameters change, whenever the dependencies change. And if these things sound familiar, these are all the things that go into the entish name of your data set. And so what we can do is anytime the data set hash changes, that becomes a new cache key. So the surprise here is that Memento already tracks all these things in the invocation hash, making it possible to do high fidelity automatic caching. And the caches, the other nice surprise is that you can share those caches with your team members, or in fact, if you put it in distributed storage, maybe even beyond. Imagine a world where anyone in the world can sort of reshare your data as long as they get to the same invocation hash. So let's take a quick look at how caching works in Memento, and then I'll close with some final thoughts. Imagine you have a function invocation with some arguments that produces a result. Well, we can start by taking the result and computing a hash on the contents of the result itself. We can take that hash and the results and place it into an output cache. So if you look, and this is content addressable storage. So if any two functions are invoked with the same parameters, you get the same result hash, and therefore you don't need to reuse the storage twice. You can actually use the same block of storage. Then we can take the source code for the function, the arguments themselves, compute hashes on those, and put them into what we call an invocation hash. That invocation hash gets packaged in the Memento, along with metadata, and then in addition to the metadata, a pointer to the result. The pointer to result is just the result hash itself. And so now you take all these things and you place them in a federated catalog of some sort, and you can imagine several catalogs that would be possible to store these kinds of mementos, maybe one day Dataverse or something else. But all you need to do is store that memento in the catalog, and the invocation hash can be computed by someone in the future who happens to try to want to compute the same function with the same arguments. They'll arrive at the same invocation hash, and therefore they'll be able to find the memento in the catalog and use that to look up the result. So this is how caching works in Memento. All right, so I've talked about Memento and how it works, and so let's take a look at some next steps. First of all, I'm pleased to announce that thanks to this conference, I finally got the approval to make Memento open source, which I'm very happy about. Thank you, thank you. And so anyone in the world today can do pip install 2sigma.memento, and you can go to github.com/2sigma/memento to see the source code and to contribute to the project. The project right now is an implementation of Memento, but we think it can go much, much further than where it is today. We think that there's potential here for it not just to be a Python implementation that works well with pandas and Jupyter notebooks and as standalone Python scripts, but to really extend it beyond that. So Larry and I are collaborating right now on a white paper that talks about the standard of Memento and how we can extend it beyond its implementation. And that opens up a whole set of research areas around this technology. So first of all, the implementation itself can be caught up with the ideas in the white paper. So this includes things like context parameters and durable storage and signature chains. Not all those things are in the current implementation, but we believe they can be added by a collaboration with other developers. In addition, we can develop new distributed compute and storage plugins for major cloud providers to make it so that your storage doesn't just go to your local disk, but it can go to S3 buckets and to other stores automatically. Then there's this idea of what if we go to major cloud providers that provide data warehouse technology, like BigQuery, for example, and see if they'd be willing to create mementos. Every time you create a new table in BigQuery, maybe you can get a memento alongside of it. That would be a really interesting area of research as well. We haven't done any cache replacement policies, so today these caches just build up and up and up. But garbage collection and replacement policies would be an interesting direction. And then more language bindings. So Java, Julia, Rust, R, you can imagine lots of technologies that could use the same standard. And then finally, there's this area that I think is really interesting. We've started to create some proof of concept around this. But the idea of creating a functions as a service that's Memento aware, so that when you run a compute, it's not just about an RPC call to some code, but the functions as a service is actually aware that you've called this function before, or someone else has with the same parameters. And so I can give you the answer, a pointer to the answer, immediately. So doing this would require an investment in doing better monitoring metrics and management to make it more production grade, containerization of functions to make sure that they're really reproducible. They grab in all of their environment. And it also opens up this idea of something that I'm calling the federated web of data, which is if you could take a bunch of these Memento servers, functions as a service, and federate them around, you can imagine almost a World Wide Web style web of data where it's not just that you have data at rest, but you actually have live compute attached to the data, and you can end up hosting all of that live compute to go with the data. So lots more potential here. I'm really looking forward to collaborating with people here and elsewhere on Memento. I thank you for your time and your patience with the AV issues that we had, especially, and I would love to answer some questions. And I think even though the mics are not on in this room, we still would like people to use the mics for questions for the AV feed, for the live stream.
So one thing you showed me a long time ago with this system, before it was open source, is that you could automatically return back the provenance, the exact thing. And that's a super powerful feature you didn't talk about. I think it would be useful to just say a few words about that.
Sure, sure. So the question was about provenance. And so yeah, Memento, as I kind of hinted at some of the previous slides, and it's hard to get into all of this in a 20-minute presentation, but when you call a function in Memento, what the system is actually doing is wrapping the function, and it's intercepting your call to the function. And if that function calls other functions, other Memento functions, then those are too intercepted. And so as you're making this call chain, Memento is tracking the parameters that you pass in, the functions that you call, and it's tracking all of the other information about your runtime environment, which version of Pandas, which version of Python, what operating system. All this is being collected into this Memento object, which contains the provenance. And since the Memento objects refer to each other, you get this chain all the way from your final result all the way back to the original ingestion functions that pulled in the city bike data or whatever it is that you're pulling in. So Memento sort of gives this to you as a property of the system itself. And again, it's not just about the implementation here. This is sort of an idea, right? That as we're doing compute, we should be recording metadata along the way so that we're tracking provenance in some higher fidelity way than we do today with just English text. Does that address your question?
Yeah, I just wanted you to say that so you can just do a query. Can I?
Yeah.
I just want to. So there's a language element to this, and the collecting the hashes and stuff. In some sense, there's, if you assume, which of course is not true, but let's pretend for the moment that containers were reproducible environments that were deterministic. Well, then can this be totally language agnostic in some sense? So if you're saying, well, hey, we had this container read this data, like if you look at what Roth talked about, well, if he has an input and an output data, right? Well, and then there's the container, and let's imagine for a moment that it ran on always the same CPUs and that we had a hash of the container. Why do I need? Could I build into the system just what you're talking about without necessarily the language? I understand how this ties Jupyter Notebook, and I'm talking too long. But it's just like there's part of me that just divorcing this from the language and just thinking about this from the system, how much of this can we just do?
Yeah, it's a good question. So like how much do you need the language, in other words, to make this happen? Or how much do you need the implementation? Could you approach it from the bottom up instead of the top down? And I've thought a bunch about this. I think the answer is maybe, or it depends is kind of the answer. So first of all, one very big caveat that I didn't fully get into is that in order for any of this to work, you have to code in sort of a functional approach. So if you have state, or if you have some ability to have non-deterministic results, perhaps you're using a cryptographic random number seed as your function. Of course, you're not going to get the same results each time. And maybe you could pretend that you could get the hardware to reproduce thread ordering and other things. But there are going to be certain circumstances where reproducibility is just not in the cards. And that's increasingly true. Like LLMs are not reproducible today, right? If you make the same query, even with a what do they call it? Not noise, but temperature. Even with a temperature of 0, in some cases, you don't always get the same results, and models can be updated and so forth. If you rely on external services, if you store state and then call the function twice, but it relies on some external state. So I don't think that you can do this without at least some support from the top down to put a little bit of guardrails in what you're doing. But I'm happy to be proven wrong. You know, if we can figure out a way to do this, you know, I was talking to someone before about like emulating, 6502 processors, and there you've only got like 64K of RAM to deal with. And if you could just capture the whole state, every single instruction, you know, maybe you could reproduce that. But you know, at some point you also have to balance with being pragmatic about it and you know, figuring out how to work. But I think it's a great research area to figure out just how do you ensure the reproducibility. One thing we're finding as we try to do this practically within 2 Sigma is that sometimes the modelers don't want that kind of reproducibility fully. They don't care about it. They care that it's close enough, and that's good enough for them. And so in fact, it's a bit of a weakness of this framework that you get, the hashes can be too sensitive. Right? If the hashes are very sensitive, maybe I don't care that it was run on AMD. Fine, it's like, you know, 6 orders of precision off or something. For my research, I didn't really care about that. So we do offer some knobs in Memento to tune these things, but it is true that this can be a source of problem. So like if you go all the way to the system level, those knobs might be harder to tune, perhaps. I don't know. I think it's a really good question, and it's worth further investigation. I think we've got a question over there. Oh, sorry. Yeah.
You talk about cache invalidation. How does that actually work? Like, you know, say with a root data set or an intermediate data set is updated. You find there's an error in it, or you need to do something to change something that has dependencies. I assume that then things get recomputed sort of down the chain to adjust for that.
Yeah, so and that's a little bit different from cache invalidation. So there's 2 things here which I want to keep separate. One is what you're talking about, which is, hey, I modified the normalizer, and therefore the joining function is going to produce different results because the joining function depends on the normalizer. So you get sort of a cascade of changes, and that's handled actually by Memento through this entish name, right? Through the name of the data set, through the kind of hash that gets generated, that's automatically handled. And actually a really neat result of this is it works really well with version control. So because it's not like a sequential version number of your data set, but it's a hash, you can actually create branches. And I've got a cool example where, you know, we have a researcher, like several researchers collaborating on the same repository, and one creates a branch and they start making changes. Well, the changes that they make will only affect the computation from that point onward in the graph, and they can reuse everything from the upstream, from the main branch, for the earlier computation. But because there's no like sequential version numbers, that just like flows nicely. The cache invalidation that I was talking about in the final slide is really more about, well, Memento's recording the result of every single computation that you've ever made. And over time, that grows and grows and grows. And so, first of all, is it always worth it to cache? Sometimes maybe not, right? Like maybe if you have 1 + 1, like you can figure out it's 2 faster than you can read a file that says, hey, the answer was 2. So, you know, you can hear me now through the mic. Nice. Let's hope that sound doesn't happen again. I'm going to have nightmares about that sound. So the cache invalidation, it's really more about can we actually evict some of that, you know, that was worth storing, because we can tell that nobody's using it anymore because there's a new version and whatever. The nice property of Memento is that because these functions are pure, the cache is literally a cache. The reason that we store the ingestions as durable data is that everything past ingestion, it can be reproduced, right? Ingestion can't. You don't know if you pull the same data from a vendor twice if you're going to get the same results. But everything then onwards can be cached. And because it's a cache, you can actually wipe the whole thing out, and you should get exactly the same results. But in some circumstances, maybe you don't want to just record and just keep growing the cache. So you need an LRU, or you need some way to evict the cache.
Thank you.
Yep. So. I don't know how we're doing time-wise. I'm happy to answer more questions as long as anyone doesn't give me the signal.
Yeah. So my question is, if you have a DAG essentially of a composition of functional transformations on your data, right? You're pretty much like 90% of the way to MapReduce, aren't you? Right. So, can you pretty much apply this same idea of realizing all the intermediate results and then memoizing them essentially? Like, is that idea extensible to stuff like MapReduce? Or with,
Yeah, that's a very good question. So yeah, MapReduce is interesting. One of the things that we're trying to do is see if we can map the concepts from MapReduce, the concepts from Spark RDDs, the concepts from the sort of distributed computing technologies that are in very common use today, and see how they would be implemented in this pattern. In many cases, it's fairly straightforward, and in other cases, it requires some thought to figure out how to do it. The main disconnect is that, especially in things like RDDs for Spark, those are stateful. They're sort of like you have a data store that's going to be manipulated in place effectively, and because you're recording state, you don't know that the second time you invoke a function, you're going to get the same result. So as long as you can structure it in a way that each stage is functional, meaning that it doesn't have side effect, it's side effect free and the functions are pure, then it will work. But as soon as you introduce state to it, that violates one of the principles here, which is really that everything is immutable, right? And everything is purely functional. So it requires a little bit of thought, but we've started looking at that, and I think the answer is that we can get to the same results as MapReduce, but it requires a little bit of attention. Does that answer your question?
Yeah.
Great.
And if we have time, a small follow-up to that is, right? If you have purely functional, like stuff like the Haskell compiler will happily do, more exotic transformations that map, that merge multiple functions together, so you don't realize every single intermediate result, right? It's like, because you have to realize every single intermediate result in order to do the memoization. Like, is that a trade-off that you find commonly worth it to realize all of your intermediates, or is the trade-off, sometimes not there?
So first of all, Haskell would be a great language for this, actually better than Python, because Python is not functional, and you can really get yourself into trouble with Python. But yes, if you're using that kind of, as long as you're using that style of programming, this works quite nicely, and all of the intermediate results actually, collect quite neatly into mementos, and you can get the provenance and everything else. So there is, in the current implementation, there is this idea of a function returning a partition, which is kind of interesting, and it lets you implement a lot of these MapReduce style patterns. And happy to connect later. I want to be, I want to pay attention to the time here. But great, excellent question. Thank you. All right, thank you very much.